Exploring Life. Chapter 4. Water. Part 2. Water's unique properties come from the presence of hydrogen bonds. These weak bonds create strong effects, allowing water molecules to stick to each other, a property known as cohesion. They also enable water to cling to other substances, which is called adhesion. Together, these interactions help explain water's behavior in everything from droplets to living cells. In this image, you see a beaker with a straw, where the water level inside the straw rises above the level in the beaker. This demonstrates the capillary effect, a liquid's ability to move upward through narrow spaces without any external force. It's driven by adhesion, which allows water to cling to surfaces, and cohesion, which pulls other water molecules along. You've probably seen this many times without realizing it, like when a bath towel absorbs water. The same principle is used by plants to transport water from their roots to their leaves, helping them stay hydrated and support vital processes like photosynthesis and transpiration. Imagine a cluster of magnets stuck together. You'd need to pull them apart to break through, right? Water molecules act in a similar way at the surface. Surface tension is the result of strong cohesive forces holding those molecules tightly together. It's this tension that allows certain insects to walk on water and enables small objects to float, even if they're heavier than water. And here's a perfect example: surface tension at work. The weight of the water lettuce, Pischistratioides, causes a slight depression in the water's surface. But surface tension pulls upward, creating a balance that keeps the plant afloat. If you look closely, you can see the subtle indentation in the water around the leaves, a clear illustration of how surface tension resists the plant's weight and holds it up. Water plays a key role in regulating temperature because of its unique structure. Before its temperature rises, additional energy must first break hydrogen bonds. This gives water a high heat capacity, allowing it to resist sudden temperature changes. It also has a high heat of vaporization, meaning it absorbs a lot of heat when it evaporates, cooling surfaces in the process. Water's high heat capacity is exactly why we sweat. As it evaporates from our skin, it carries excess heat away, helping to regulate body temperature. Plants use a similar process. Through transpiration, water evaporates from the surface of leaves, cooling the plant and helping to regulate moisture and temperature in the surrounding environment. But think bigger: this same property of water helps stabilize the temperature of entire ecosystems, including lakes, forests, and oceans. It even plays a critical role in regulating Earth's global climate. One of water's most unusual properties is that its solid form, ice, is less dense than its liquid form. This happens because hydrogen bonds lock water molecules into a rigid, open crystal structure when it freezes, making ice expand and float. It may seem simple, but this is crucial for aquatic life. Floating ice insulates the water below, allowing organisms to survive even in freezing conditions. Without ice cover, many aquatic ecosystems would collapse in winter. This illustration shows the difference in water molecule arrangement between the liquid and solid states. In liquid water, molecules are closer together, while in ice, hydrogen bonds, shown here as dashed lines, hold the molecules in a more open, rigid structure. As a result, ice is less dense than liquid water, which is why it floats. You can see this principle in action in the photo below, where ice floats on the surface of the ocean. Water is often called the universal solvent, and for good reason. Its polarity and ability to form hydrogen bonds make it excellent at dissolving many substances. Ionic and polar molecules dissolve easily in water, forming what we call aqueous solutions. This property is essential for biological and chemical processes, from transporting nutrients in our blood to enabling reactions inside cells. And you use it all the time, when washing your clothes, cleaning dishes, or rinsing off your car. Water is dissolving and carrying away all kinds of particles. This image shows what happens when table salt, sodium chloride, dissolves in water. On the left, you see the crystal of NaCl, made up of alternating sodium and chloride ions tightly packed together. As the salt dissolves, water molecules surround each ion. In the center, notice the hydrated sodium ion. It's surrounded by water molecules with the oxygen side facing in. That's because sodium is positively charged, and oxygen has a partial negative charge. On the right is the hydrated chloride ion, surrounded by water with the hydrogens facing in, since they carry a partial positive charge. This attraction between water and ions pulls the crystal apart and keeps the ions separate and dissolved in solution. Each ion is fully surrounded by water molecules. We call this hydration. This ability to surround and separate ions is essential for nutrient transport, nerve signaling, and countless cellular processes. Obviously, the chemicals dissolved in water are a big deal when it comes to water quality, but some of them don't just affect what's in the water, they actually affect the water itself. Water molecules can dissociate into hydrogen ions, H, and hydroxide ions, OH. In pure water, these ions are balanced, resulting in a neutral pH of 7. Acids increase the concentration of H ions, lowering the pH, while bases increase OH ions, raising the pH. To maintain stability, biological systems rely on buffers, substances that absorb excess H or OH ions. Buffers help keep pH levels within a narrow range, which is essential for life to function properly. This figure illustrates the initial stage of water ionization. It shows how a water molecule separates into two parts, a hydrogen ion, H, and a hydroxide ion, OH. This process, though it occurs in only a small fraction of water molecules, is fundamental to understanding pH and the chemical behavior of water. The pH scale quantifies the concentration of hydrogen ions, or H, in a solution. It ranges from 0 to 14, with 0 being the most acidic and 14 the most basic. A neutral pH is 7.0, which is the balance point between H and OH ions. Extreme pH levels, either too acidic or too basic, are often inhospitable to life. For reference, the pH inside most cells is around 6.8, blood maintains a pH near 7.4, and the stomach is highly acidic, with a pH between 1 and 3.5 to 8 in digestion. This diagram shows the pH scale, which measures how acidic or basic a solution is. Understanding pH is essential in biology because even small changes can affect how catalysts known as enzymes work, cells function, organisms survive, or even how well our planet's ecosystems stay in balance. Water is often taken for granted, yet it is anything but ordinary. From the birth of Earth and the Moon to the search for life among the stars, water shapes the conditions that make worlds habitable. And on a much smaller scale, it is the essence of life itself, an essential part of every organism, flowing through each cell and carrying the chemistry of life. So water is not just a substance. It is the thread that weaves together stars and planets, ecosystems and organisms, the universe and us. Now that we've explored water's unique properties and their importance to life, take a moment to reflect on what you've learned. And if anything feels unclear, go back and review. Mastery comes through reflection and repetition.